I want to talk about electric generators. This is the way we produce electricity. This is the way hydroelectric plants work. This is the way when you put gas in an electric generator, this is literally what they do. You have some magnet here, a couple of magnets creating a magnetic field, and then you'll have this loop that we force to rotate mechanically. Like you could do it by hand. You could crank it by hand. The starter on your car does this. It uses gas and a little bit of charge from your battery to get going. Or I guess a better way to say this is your alternator does this. The alternator belt turns this loop through a magnetic field, which creates current. Depending on how you set up this loop here, what we call these brushes here, you can make this do a direct current or an alternating current. It's actually pretty easy to turn it into one or the other. And that requires work to do. You don't get this current for free. It requires work to convert chemical energy or mechanical energy into electrical energy. And the reason this does this is we have a changing flux through this loop. We talked about this last time. Remember, flux is B times A times the cosine of the angle between B and the normal vector. So if your normal vector is always changing, your angle is always changing. So we have a changing flux that creates a current. Okay, now we want to talk about inductance. So say I have some changing current flowing through a coil. So I've got some current flowing. And I make that current, or make that circuit into a loop like this. Well, then I'd have current flowing around like this. That's a solenoid. That creates a magnetic field that would point this direction. Inside those loops, we get a magnetic field. If that current is changing, then I'll have a changing magnetic field in these loops. Changing magnetic fields create new currents. So by allowing I to change here, we can create new currents here in these loops. And if I is increasing, so if I is going up, then my magnetic field here would be going up. That changing magnetic field creates a changing flux through each of these loops that oppose that increase. So that would create an induced current going backwards. And if I is going down, then I'd have a decreasing flux. I would have an induced current that would flow forwards. We call this thing an inductor. And an inductor, it's a circuit element that we put in our circuits like resistors and capacitors. Inductors are cool because they don't resist current. They're not resistors. Inductors resist changes to current. That's going to be one of your homework questions. Inductors resist changes to current. We put these in circuits when we want to try to keep our circuit or current stable, where we want to avoid big giant changes in current. So if my current is going up, this thing says, I don't want you to go up too quickly. I'm going to try to resist that. So my current's flowing this way. It tries to resist that change in current. So this thing kind of acts like a resistor. If my current's going down, this thing tries to make up for what we're losing, and it kind of acts like a source or like a battery. Okay, and our formula here, is right here. where L is called the inductance of that inductor. So L is inductance. It's measured in Henry. And our formula for our inductance is d phi dt equals L di dt. So there are the units for inductance: Tesla meter squared per amp, Henries. And our induced current goes opposite to the change in current. Negative L di dt. So I'm not worried about this numerically. I'm worried about this conceptually. The induced current tries to stop you from doing what you're doing. It goes in the opposite direction of the changing current. If your current's going up, the inductor tries to stop you and goes backwards. If the current's decreasing, if d I dt is negative, then your induced current will flow in the same direction that current used to flow in to try to make up for that loss. If you put a bar here, some conducting material, a lot of inductors have these in there, you can increase the inductance, you can increase the value of L here and make this more inductant and have a stronger inductor. Okay, so there's just, okay, this is interesting. So what happens if we get this circuit, I've got, nothing's hooked up yet, I haven't started the current, I've got just a resistor and an inductor and a battery. And then I hook it up and I let it go. Well, we go from zero current to suddenly having current. That's a changing current. That's a pretty steep change in current. This inductor doesn't like that, and it tries to resist that. It kind of acts like another resistor. So my current is going to flow pretty steeply at first, but this inductor tries to level that off. And that's what the point of the inductor is, to level off the current. So as the current gets bigger and bigger, but with a smaller derivative, we'll eventually asymptotically approach this new value, epsilon over R, where epsilon naught here is that value that we had here, our induced current. So we asymptotically approach this maximum current. Now, what if we unhook that battery? What happens? So now we've got a current flowing and we stop the battery. Well, now the current suddenly stopped. It doesn't like that. Inductors don't like changes. So we would go from having a relatively big current, and the inductor tries to stop that. Instead of the current stopping suddenly, it will slowly decay off. Energy. Oh, here I can go back to this picture. Last thing I want to mention today is mutual inductance. So you have two different circuits here. Separated by space. So you've got, let me draw these guys out. Over here, I've got some alternating current, maybe some current that's changing with time. This guy is creating a magnetic field that points out from him. Over here is just a wire. A changing current here will create a changing magnetic field that will create changing flux through this current or through this circuit, which will then induce a current over here. So a changing I here induces a current over here. This is called mutual induction. This, of course, by the way, this will be changing with time, which then will affect back this guy. And these two, they kind of fight back and forth until they reach an equilibrium. But the point of this process is by changing the current over here, I can induce a current over here without these two things touching. This is how your wireless toothbrush charges. You've got your base and it's got a coil in it. And then you've got your toothbrush. Those coils do not touch. That coil when your toothbrush is inside it because you get it wet. You don't want to ruin it with water. So you just get these close to each other and your base has a changing current and that induces a current in your toothbrush, which charges your battery. This is the way those pads work where you got a pad and you just set your cell phone on it and it charges your cell phone. It's the same idea. You're not actually hooking up to the circuit, you're charging through mutual induction. But this effect drops off pretty quickly with distance. I think I mentioned this before, but if you ever read anything about the scientist Tesla and how he was misunderstood and he tried to offer the world free energy and whatnot, this was the idea he was trying to use. He had a couple of other crazy ideas, pulling energy out of the ionosphere that were just ridiculous. But this is what he wanted to do. He wanted to build these big giant towers and charge things at a distance. The problem is this drops off significantly with distance to the point that there's so much energy loss, it's not worth doing. That's why you can't charge your toothbrush from across the room. You have to have gigantic changing currents here. All right, so that will do it for that chapter. Next time we're going to do alternating currents and Maxwell's equations. We're going to write those all down in differential and integral forms, and we're going to do Ampere's law. Then you'll be ready for test 3. I'm going to stop the recording.